Uh, Friends, we should start the session now. We have two illustrious speakers. Our first session, first presentation is by engineer Apurva Parikh from Ahmedabad, India. Apurva Parikh is a director of Multimedia Consultants Private Limited, a 40 years old infrastructure consultancy firm based in Ahmedabad. He is one of the major consultants in India, not only in Gujarat. Incidentally, Gujarat is a state where from our Prime Minister belong. Apurva completed his civil engineer's degree from Ahmedabad and then his master's at the University of Illinois at Urbana-Champaign. And while doing his post-graduation, he worked as a graduate research assistant at U.S. Army Construction Engineering Research Lab in Champaign, Illinois, USA. He has 26 years experience practicing as a civil engineer. Apurva worked in Aon Risk Technology, Chicago, USA as earthquake risk analysis engineer for some time after his graduation, and then he moved to India in 1997 to become one of the premier most consulting companies. During his career of more than 2 decades, he has worked on several notable projects, BRTS, then Special Investment Region, Rajkot Smart City, IIT Gandhinagar campus, bridge projects in Abu Dhabi, water supply and sewerage projects in Ahmedabad city, water supply in Surat city, and Samudra Darshan Path. This is something very special that he is working on now. Samudra Darshan Path, cyclone protection measure. Yesterday we saw in New Orleans how the walls have been built up. He has done some similar work like that, and probably we'll get to know something more about this in his lecture. Various coastal structures such as jetties, ferry wharves, bowstring girders, steel bridge at Bhopal. And Bhopal is one of the capital cities in India. And then Mahatma Gandhi, all of you know Mahatma Gandhi Ashram Precinct, development project, and so many others. Apurva is interested in developing civil engineering design methods based on AI platform and improving efficiencies through the use of BIM, 3D, 4D, and 5D, and lean management. He is a co-opted member of the Gujarat Council of Professional Engineers appointed by the government of Gujarat. He is a chartered engineer. He is a fellow of the Indian Association of Structural Engineers, member of Indian Roads Congress. Indian Roads Congress is one of the most powerful institutions in India who's making roads and looking after roads directly under government of India. Member of ACA, of course, member of ASC, and so many other things, but now I'm eating in his time. So, Apurva, please.
Yeah, good afternoon, everyone. I'm going to be talking about a project which is right now under construction in the city where I live and where I work. To give you a little bit of idea about India, because I don't know if you know about it. We are about almost 1.5 billion people now, more populous than China, and we have 300 cities in India with a population more than 100,000, 12 cities with a population more than 1 million people, and growing very fast. So there is a lot of pressure in urban areas. Space is a constraint. So as civil engineers, we try to look at solutions to solve problems which might improve the lives of people. And we are, this project is basically, it's a canal project which we are working on. where it's planned to have a mixed-use development on top of the canal. I'll go through some of the aspects of the project. So this is what we call an urban rejuvenation and transformation project, where we are transforming an open concrete light canal to a reinforced concrete box. This is to improve the water flow management and also minimize the environment impact and mainly improve the quality of life of people in India. This is a 110-year-old canal which was built when the British ruled India, and from that time till now, things have deteriorated. Earlier it used to be through an agriculture area, but now you can see it's passing through a very dense, developed urban area, which had a lot of issues issues which needed to be addressed as part of the project. We have about around 15 miles of such canal passing through the city. This is how the canal looks. You can see the kind of development along the canal. It's an extremely dense area, very high density, a mixture of residential areas, a mixture of a lot of factories, the industries, and with narrow roads on either side. So narrow roads on either side, limiting the accessibility of the area. So the idea was to find a way to cover this canal. So this is the stretch, first stretch of 8 miles, which was taken up. It was divided into 5 parts to execute, and almost more than 50% of the work is right now complete. So these are the hydraulic features of the canal. It was an open canal with a top width of 20 meters, 3.5 meter depth, and it needed to carry about 72 meter cube per second of water through it. The problem with the canal is, it's a canal in embankment. It divides the city, developed city, into 2 low-lying areas, and thus it's becoming a barrier for the connectivity to carry water and for the stormwater and the sewage disposal in the area. Other problem is the areas on either side of the canals get flooded during the heavy rains, and really causing economic loss at that time. Yeah, garbage is a big problem. People throw garbage in the canal and don't keep it clean, thus resulting in a lot of health issues in the area. Because of high pressure of urban development, a lot of unauthorized sewage also goes into the canal, causing a lot of problems to people who live along the canal. Some of the key issues of the project is that this is like a storm drain come a canal. So in India, as you know, we have a monsoon. So it's about 3 months a year we have rainfall, not during the remaining part of the year. So we have 3 months of very heavy rainfall, during which all the water is to be disposed from the urban area. So this is a storm drain come canal. Irrigation water also needs to be released at regular intervals, because there is a lot of agriculture going on the downstream of these canals, where farmers are dependent on this water. There is a very dense development on either side. So anything we needed to do to the canal was to ensure that whatever we do does not damage the buildings and does not affect the safety and the accessibility of the people who live along the canal, because there is not many other accesses to approach this area. Some of the things we did was because we had to carry stormwater as well as irrigation water, it was decided that we would provide separate conduits for the stormwater drains and the irrigation water. The irrigation water conduits would be precast concrete boxes to carry irrigation water, and that would be done first, and then the in situ casting of the stormwater boxes would be carried out at a later stage. So that's what we did, a precast combination of the precast and cast in situ boxes. This was to reduce the time for the closure of the irrigation water, and to ensure the safety of the properties along the side and to carry out work in between, we decided to provide reinforced concrete diaphragm walls on either side. So that would, ensure safety of the adjacent structures, which are most of them not engineered structures. So that would be a problem in case of we do some excavation. Even with protection, there was an issue of the stability of those buildings. You can see how dense this area is and the amount of buildings on either side of the canal with very little space to work. Yeah, so this is how the cross section looked. So we have the precast boxes to carry the irrigation water, which pass through the center of the canal, and then we would have the stormwater boxes. We are enhancing the capacity of the canal. We are deepening it to allow for the stormwater from the adjoining areas to come in and flow to the disposal point. So yeah, this is how the canal looked, and this is what we did. We provided the diaphragm walls on the either side first. After that, the area was excavated to the required profile, and this was followed by the placement of the reinforced concrete pre-stressed boxes on the in the middle portion. So the idea was that after we place these boxes, and if the irrigation water, if the farmer needs water, these areas would be dammed, and the work could go on in this area, and the required water would flow through these central boxes to allow farming to continue even during the construction. So that was the whole idea. Yeah, and so this is just one sample. Actually, there is a lot of things being planned by the planners on top of this. There will be activity areas, there will be roads in some stretches. So the whole idea was to create an area which is useful for the people and clean and safe. These are some of the photographs of the work. So as you see, we have this deep 2.6 meter by 2.6 meter boxes. So the diaphragm walls are first constructed. You can see traffic is allowed to move on either side. And we have 2.6 by 2.6 meter boxes placed in the center. Another photograph, how the work was carried out. This is huge. This is probably one of the largest size of box used in our part of the country. For the first time we designed and we got this kind of size of boxes fabricated. These boxes needed to be watertight, so we had a system where we were making sure each and every joint in the box is watertight. The length of the box is about 1.5 meter or 2 meter sizes, which were used to placed, and the joints have been sealed. So once the boxes, the precast boxes were placed, and the work of the in situ box was done, afterwards you can see the amount of people, the challenging area, environment in which the work was done. There are people living here, there is so much traffic on either side, and we have to do the work with this kind of people and ensure safety. These are some other photographs. where we also have done work of the precast boxes on curvature, and we have, basically we have some in situ joints as well as access chambers for access to the boxes for maintenance. And these are some more photographs. The precast box were casted about 50 miles away from the site. There's no space near the site, so this is showing you the manufacturing facility stockyard where the casting and the manufacturing of the boxes was carried out. We were able to cast about 40 boxes a day, so that amounted to around 60 meters. 60 to 80 meters of boxes every day. This is some of the other photographs of the work which we carried out. One of the challenges was bringing these boxes from 50 miles through a very heavily traffic dense area. So most of the transportation of the boxes happened at night, and only it was stacked in a nearby stackyard, after which the boxes were brought to the site and erected. For the jointing of the boxes, we had the galvanized iron flange bolt system. We had rubber gaskets in the tongue and groove joint. And apart from that, there was 3 or 4 layers of different material like non-shrink grout, and also, if required, we were using epoxy mortar to seal each and every joint so that we ensure a watertight, leak-free system. So this is a photograph of the waterproofing works which we did. Yeah, another picture, and these were the locations from where we had the access chambers for the people to access the box. This is yet to be casted in this picture, so we would have some manhole access ladders to go in. So yeah, this gives you an idea of the kind of work which happened and the kind of area in which this kind of work happened. So it's also it's a very well appreciated and received project in the city, and one of the longest such canal closure projects carried out in India. Right now we have done about 8 miles of this work, and ultimately when completed it will be 15 miles of such canal within the city which will be closed. There have been a lot of questions regarding sustainability and use of such a large quantity of concrete, but this was inevitable. We had to do it because in the short term the city did not see any other solution than doing this. Yeah, so this is a part where they have constructed a road on the top, and yeah, a lot of media attention. People are very happy with the work. So some of the technical details of the project. So the precast box is 2.6 meter by 2.6 meter. The grade of concrete was M50, which is cube strength, 50 megapascal. And reinforcement was 500 MPa yield strength. The cast in situ boxes are 6 meters by 3.3 meters, so about 20 feet by 10 feet, and with a grade of concrete of 30 megapascal, and again same reinforcement. Diaphragm walls constructed on either side were 500 millimeter thick, 10 meter depth. Again, grade of concrete was 30. So design standards which were used. So in India, we have the Indian standard codes for plain and reinforced concrete design. which is similar to ACI 318, and which is the IS 456. But because this structure is designed to carry the vehicular loads, vehicles on top, we have to follow the Indian Roads Congress standard when we design this kind of structures, because the loading has to be Indian Roads Congress, and we have a design code called IRC 112. This is a recent code, 2014, and it's very similar to the AASHTO LRFD code. So this is basically what we call in India limit state design, which is similar to the LRFD design which you have in US. So we have the limit states of, strength, the limit states of equilibrium, limit states of serviceability, and limit state of fatigue now. So this is what the structure is designed for. A little bit about the precast boxes. So yes, precast boxes were built using self-compacting concrete. It's a state-of-the-art plant because we have to do in the first phase, we have to do about 15 miles of boxes. So, the molds were created by a Japanese company using automobile, steel, basically, so which would give us more reputations and a very good quality. The reinforcement cages were done using the automatic rebar bending machines, and it was, of course, steam cured to give us the required numbers per day which we required. And installation was done using, the state-of-the-art equipment, and to make sure that we got it in the right levels, because otherwise the joints would not match. Jointing it's a tongue and groove joint. I already talked to you about the type of, measures we took to ensure that we got a watertight joint. A little bit, very briefly, about the kind of loads used for design. So dead loads, superimposed dead loads, live loads, water pressure, temperature, and earthquake. These are the loads we need to use for this kind of, structural design. And yes, this is what we have in India, similar to what you have, the HS20, I believe, or similar thing you have in AASHTO. So these are our vehicular loads. We have a 70-ton, tracked vehicle which we used, and then we have a train, which is a 100-ton train. So 100-ton train, this is the longitudinal spacing, and this is the different, transfers arrangements for this train, which we need to use to find the worst, the worst loads which would be critical for design. And for the smaller box, we also have a 20-ton, what they call a single axle load, and what we call a bogie axle, which is 20 plus 20 tons. For when you design smaller spans, you need to place 40 tons on top of the box and design for that. And yes, similar to AASHTO, we have our load factors and the partial safety factors which we apply to apply when we are doing the design. So some of the highlights of the project: total length of precast box, 25 kilometers, that was 15.5 miles. Total quantity of concrete which we used was 255,900 cubic meters. We used about 33,200 metric tons of steel, and we had total quantity of diaphragm wall was 255,000 square meters.